Just as the oceans opened up a new world for clipper ships and Yankee traders, space holds enormous potential for commerce today. The market for space transportation could surpass our capacity to develop it. Companies interested in putting payloads into space must have ready access to private sector launch services. The Department of Transportation will help an expendable launch services industry to get off the ground. The space age is barely a quarter of a century old, but already we've pushed civilization forward with our advances in science and technology. We want our friends to help us meet these challenges and share in their benefits. NASA will invite other countries to participate so we can strengthen peace, build prosperity, and expand freedom for all who share our goals. We can reach for greatness again. We can follow our dreams to distant stars, living and working in space for peaceful economic and scientific gain. Tonight, I am directing NASA to develop a permanently manned space station and to do it within a decade.
"15 years earlier, July 20th, 1969. The entire world lies transfixed as two human beings, Neil Armstrong and Buzz Aldrin, stretch their legs on another world. Buzz fields out new methods of locomotion in front of the camera, showcasing a variety of hops and gaits in the 1/6 gravity, airless environment of the moon. In his and Neil's ear is one voice.
Columbia, this is Houston, over.
One person whose job it is to relay the will of mission control to the astronauts in the field. A kind of celestial liaison, a bridge between the controllers and the crew. This is the Capcom, or Capsule Communicator, and tonight, it's astronaut Bruce McCandless. A member of the Green Team, he's recently relieved Charlie Duke, fellow astronaut and member of the White Team. McCandless works under Flight Director Cliff Charlesworth, as the operational apparatus nervously counts up the seconds and minutes Neil and Buzz spend walking around outside. A single failure in their suit, a seam ripping open, or a valve popping loose, and they may have only seconds to save themselves. Neil and Buzz aren't tethered to their lunar lander. Their life support comes from their backpacks, and the 1/6 gravity on the moon's surface is more than sufficient to keep them from floating off into space. It wasn't that long ago that American astronauts were struggling and wrestling with large and chunky umbilical tethers that both kept them attached to their spacecraft and fed them the things they need to survive. Project Gemini, which terminated the same year Bruce McCandless joined NASA, made several attempts to implement spacewalking technologies that, while noble, were both recklessly ambitious and arguably irrelevant to the experience required for lunar exploration. The prime example of this is the Air Force's AMU, or Astronaut Maneuvering Unit. Part of a military strategy to build a space station in low Earth orbit called MOLE, or Manned Orbiting Laboratory. The AMU is a hot-firing hydrogen peroxide-powered jetpack with a delta-V potential of 76.2 meters per second. In other words, the operator could exhaust all of its onboard fuel and accelerate from a relative stationary 0 to over 170 miles an hour. But on its maiden flight, Gemini 9, Gene Cernan didn't get to test the AMU, because by the time he got to it outside the spacecraft, he was breathing and sweating so hard that his air-cooled spacesuit couldn't keep up, and his helmet visor fogged over. That pretty much put an end to further AMU testing, despite an attempt to fly it on Gemini 12. NASA would eventually inherit many of the Air Force pilots selected to fly on Manned Orbiting Laboratory. 7 of them would become NASA astronauts the same year Bruce McCandless talks to Neil and Buzz on the surface of the Moon, joining 11 scientists who signed on in '67. McCandless, a cohort of the 19-man group of 1966, would watch over the months and years as one by one all of his peers were selected for flights and flew into space. As time dragged on, programs got cut. Apollo applications, which started at a mind-boggling 45 manned flights, was cut down to only 3. 3 long-duration missions to the space station known as Skylab. AMU testing continues. A watered-down version, the Automatically Stabilized Maneuvering Unit, or ASMU, designed to be flown inside the Skylab space station, uses so-called cold gas, simple pressurized puffs of nitrogen, much safer than the combustive hydrogen peroxide, but also much weaker. There was even a foot-controlled maneuvering unit, as well as a handheld unit similar to what was already flown in Gemini. However, Skylab's exterior is an ungainly and unforgiving place. A network of struts and scaffolding with delicate solar panels make it a poor environment to test jetpacks. The technology just wasn't ready, and NASA didn't yet have a vehicle that was well suited to the task. Therefore, the entirety of testing occurs inside the station. The ASMU backpack, designated Experiment M509, passes its test with flying colors. Increasingly miniaturized stability control systems allow the jetpack to offer automatic heading hold functions, freeing its astronaut operator to use both their hands. It was a technology slowly maturing, the promise slowly outweighing the risks.
You hear the puffs, that's the nitrogen gas. There's the hand controller in close-up. Bill is going to make a little correction now with his attitude. The hand controller over on the other side, by his left hand that you can see now, it looks like a T, is called a T-handle, and that's the translation hand controller. And Bill will be using that to stop his drift once he gets up there. Right now, he's using the rotational hand controller to maneuver himself in a position so that he can insert the fireman's pole in his slot up there.
Bruce McCandless, assigned to assist development on the device, signs off on documentation affirming its potential, recommending it for use on future manned spacecraft. McCandless, just 28 at the time of his selection in 1966, finds himself, by the time of the final flight of an Apollo command module some 9 years later, the only member of his class who had not yet been selected for a flight. Like Buzz Aldrin, McCandless is undeniably brilliant, but introverted. He has a strong self-reliant streak that comes across as antisocial. He also comes from relative affluence. He isn't a test pilot, nor is he a scientist. Occupying an unhappy medium between these two extremes, Bruce McCandless finds himself an astronaut without a mission. He gets close in 1973, serving as the backup pilot for the first crewed flight to Skylab. But after 1975, with the space shuttle now stuck in development hell, it would be a long time before American flights into orbit would resume.
Skylab was only the beginning. We are on the verge of an era when man will launch a whole new generation of manned space laboratories regularly served by shuttles to carry scientists, technicians, experiments, and supplies between Earth and space.
You can see the
America's first space shuttle.
tremendous
Shuttle has
clouds that
cleared
just
the top.
billowed forth from it. And look at it rising. It looks like a statue going up, doesn't it?
It surely does. It's just a perfect plume coming out of those rocket engines.
You can see it roll there, too.
Those solid rockets that are attached to the sides are, I believe, somewhere around 12 feet each in diameter.
The biggest solids ever built, yes. They are 12 feet. And the solids are considerably longer than either the external tank or the spacecraft itself.
It's just too bad that everyone couldn't have been here today, although I will admit it was very crowded, but it is a spectacular thing to view and be part of in person. Frank, I think you felt like we did here about 30 seconds before the launch. The atmosphere, you can feel some kind of electricity in the air out here, no matter whether you're 2, 3, or 4 miles away, and I'm sure the people on the causeway out there felt the same thing. There's an element of excitement, of pride, of prayer, and it's like we all go up. It's like everyone here was just helping that 7 million pounds of thrust.
Yeah, everybody's kind of pushing and pulling at the same time, yes.
It's the 1980s, and the shuttle is finally here. After years of delays and setbacks, the early shuttle program fills many with an intoxicating optimism. Finally, a robust spacecraft that takes off like a rocket but lands like a plane. A multi-mission glider with a payload bay large enough to make NASA's eyes water. This was a remarkable achievement. Now, America had a vehicle that could actually undertake new missions in space, missions it wasn't specifically designed to fly. Shuttles could both deploy and recover, build and deconstruct, retire or repair. It could launch probes to the outer planets, or function as its own Earth-orbiting laboratory. It could fly 7, even 8 people at a time, and it could do it over and over again. At least, that was the idea. The shuttle bent, and in some cases broke, many of the self-imposed safety rules established in the late 1950s when space travel was rightly feared for the engineering challenge that it is. Its main engines are cutting edge. They operate at 6,000 degrees. The turbopump that drives propellant spins at 37,000 RPM. It's such an advanced engine that many fear it's not fully understood. What would happen, for instance, if a microscopic fracture in one of the turbine blades began to propagate? The shuttle supplements these engines at launch with 2 humongous solid rocket boosters, which cannot be shut down or throttled once ignited. These boosters aren't large, continuous pieces either. They are segmented, joined together by rubberized gaskets called O-rings, which flex and bend during flight. The shuttle's heat shield consists of several thousand lightweight foam tiles and thermal blankets, fragile enough to be easily damaged with your bare hands. The vehicle lives on the bleeding edge of safety. Its massive wing area, required for its smooth landings, becomes in orbit an easy target for micrometeoroids and debris. But these facts, and the compounding operational costs associated with them, do not yet define the shuttle in the early 1980s. Instead, a triumphant and resurgent NASA has once again captured the imagination of the American public. The promise of the shuttle's utility in orbit brings with it a new kind of mission and a new kind of crew. Pilots and commanders are, for the first time ever, outnumbered by a new role: mission specialists. Scientists and engineers flying to space not as operators of the vehicle that carries them, but dedicated to the payload stored on board. Skylab had brought into sharp focus the need to repair broken systems in space. The 3 crews that lived there were constantly repairing it. The Jetpack concept remains a prime candidate for enabling astronauts to reach and repair parts of their vehicle without restraints or handholds. However, over the course of the shuttle's own development, a new enemy began to emerge against it: the robotic arm. The shuttle's development brought with it the introduction of a remote manipulator system, or RMS, designed to leverage the orbiter's great mass to move large and heavy objects around, such as the various pieces or modules of a space station. This articulating appendage might also serve as a mobile astronaut workstation, moving humans around to various points without necessitating a risky, untethered spacewalk. The MMU and its prime advocates, Air Force engineer Charles Whitsitt Jr., NASA's Bruce McCandless, and Walter Bollendonk of aerospace contractor Martin Marietta, had to prove that their 15-year project had its own niche to fill. By 1979, the device had better hand controls, smaller components, faster computers, and lighter materials. It was, by all accounts, on a trajectory to become a prized asset in the shuttle's arsenal. In 1980, NASA awards a $26 million contract to Martin Marietta, and the Jetpack, now called the Manned Maneuvering Unit, would be slated to fly into space aboard the shuttle. This comes at a critical point. The shuttle's heat shield tiles keep falling off in glide tests. Some fear it may be necessary for astronauts to use the MMU to access the orbiter's underside and repair the tiles themselves prior to re-entry. However, a new superglue seems to fix the issue for now. MMU would have to prove itself against the robotic arm in a battle for relevance. Bruce McCandless finally had a project to which he was inextricably attached, greenlit for flight. After 18 years at NASA, the age of 46, he was finally going into space.
I went through training in geology and spacecraft operations and the theory of orbital mechanics, things of that sort, in addition to also working as a communicator, supporting, it turned out, Apollo 10, 11, 14, and all of Skylab before the Space Shuttle program came along, and I finally got 2 missions there.
In February 1980, a Delta rocket launches a satellite called Solar Maximum Mission, or Solar Max for short, into orbit. Its purpose is to study the Sun. In the 1970s, several incidents occur which make it clear how important the Sun's influence is on our space program and planet. In the summer of 1972, between the missions of Apollo 16 and Apollo 17, an ionizing solar flare sweeps past the Earth, strong enough to irradiate a human crew and the sensitive electronics of their spacecraft had a mission to the Moon been underway. This lucky near miss is followed by higher than expected solar activity in the late 1970s, which interacts with our planet's high upper atmosphere, imparting greater than predicted drag on the space station Skylab. It was believed, once the shuttle was operational, it could be used to boost Skylab into a higher orbit and build upon it as a large backbone of an expanded American space station. These plans, however, are dashed when Skylab's orbit unexpectedly decays and the 100-ton monster comes crashing down to Earth over the Indian Ocean and Australia. Our home star has a much greater effect on spaceflight than we ever gave it credit for in the 1960s. And being able to monitor and predict its behavior will be crucial for longer duration missions above the atmosphere. However, the Solar Maximum Mission is cut short when by that November, just a few months into its years-long design mission, optical instruments and electrical components begin to fail. The good news is that Solar Max is built on a new kind of satellite chassis called the Multi-Mission Modular Spacecraft, or MMS. In order to save money, NASA has developed a new form factor for satellites, sharing parts and components and bringing production line assembly techniques to the space program, something the Soviet Union was already doing, most famously in its 3MV interplanetary flyby probes. Instead of developing bespoke parts from the ground up, an entire family of missions could share the same basic design. And this design could be made compatible with the upcoming Space Shuttle, featuring grapple fixtures and trunnion pins that would allow shuttles to regularly deploy and recover these vehicles. There was just one problem. Solar Max was slowly spinning. Its onboard electrical failures forced ground controllers to adopt an induced gyroscopic stability to keep its instruments pointed towards the sun. The 326-pound, or 148-kilogram, 24-thruster, battery-operated jetpack known as the MMU, many are convinced is just the answer NASA needs. But first, it would have to be tested. McCandless had his mission. He would be the first to fly untethered in outer space. After STS-9, NASA changes the mission numbering system to better reflect the growing complexity of the shuttle's flights. Flight number 10, which will fly in February 1984, almost 4 years to the day of the launch of Solar Max, is redesignated STS-41B. The first number, 4, is the last digit of the year it is to launch, 1984. A second number refers to the launch site, 1 being the Kennedy Space Center in Florida. A second location, Site 2, is out of Vandenberg Air Force Base in California. Still under construction, it will be some time before any shuttles are able to launch there, mainly for the purpose of achieving polar orbits. Finally, the B on the end reflects the fact that it is the second launch in fiscal year 1984, which starts on October 1st, 1983. Since STS-9 flew in November of '83, that would make STS-41B the second mission in the time frame, hence the B and not an A. Under the new system, 41B would be followed by 41C, 41D, 41E, and so on until October 1st, when it would switch to 51A, 51B, and so on. Many allege the switch is due to superstition, to avoid any mission being designated STS-13. Shuttle Flight 10 will be commanded by Vance Brand, fellow Group 5 astronaut and veteran of Apollo-Soyuz. The pilot is Robert Gibson, also known as Hoot. McCandless is one among 3 mission specialists. His partner is Robert Stewart, who will be assisting him in checking out the MMU on its first flight into space. Finally, Dr. Ronald McNair, an MIT-trained astrophysicist, will oversee the deployment of 2 commercial communication satellites unrelated to the MMU activities. These are a pair of essentially identical Hughes communications platforms, weighing some 1,400 pounds or 630 kilograms each. That weight does not include a solid rocket kick motor known as a PAM, or Payload Assist Module, which will boost each satellite into its respective geosynchronous orbit, high above the shuttle's own operational ceiling. The first satellite is called Palapa B2, a national telecom satellite for the Republic of Indonesia. The second is called Westar 6, a communication satellite for Western Union. The 5 astronauts will be flying aboard the orbiter Challenger on its 4th mission into space. After STS-9, Columbia, the flagship of the shuttle fleet, is tired and due for a refit. It will only fly into space once more over the course of the next 5 years as it gets some much-needed TLC. A third orbiter, Discovery, will be joining the fleet in the next few months, followed by a fourth, Atlantis, in 1985. It will be up to Challenger, however, to fly these crucial missions to repair a satellite gone haywire. For Mission 41B, the primary objective will be to give the MMU its long-deserved shakedown cruise and test rendezvous and satellite grappling methods required to wrestle Solar Max and bring it under control. If everything works, NASA is confident it can attempt a repair of Solar Max on the very next mission.
Security Specialist Gene String will be escorting the crew out, led by Vance Brand, Bruce McCandless, Ron McNair, Bob Stewart, and finally Hoot Gibson. They'll board the astronaut van, a converted motorhome, which will take them out to the launch pad. Accompanying the crew also astronaut John Young, who will fly our weather airplane this morning, and the Director of Flight Operations at Johnson Space Center, George Abbey, also with the crew. T-minus 2 minutes, 20 seconds and counting. Fuel cell ground supplies have been terminated. Challenger now completely on internal power, running off its onboard reactants. T-minus 2 minutes and counting. Coming up on liquid hydrogen replenish termination. Go for ET pre-press on the liquid hydrogen tank. Vehicle now isolated from ground loading equipment. Beanie cap now being swung out of the way in preparation for launch of 41B on time at 8 a.m. Eastern Standard Time. T-minus 1 minute and counting. Sound suppression system now armed. Hydrogen burn igniters also armed at this time. T-minus 50 seconds and counting. Solid rocket booster development flight instrumentation recorders going to record mode. T-minus 42 seconds and counting. T-minus 38 seconds. Orbiter computers positioning vent doors to launch configuration. Coming up on a go to take over control by the onboard computers. And we have a go for auto sequence start. T-minus 23 seconds and counting. Orbiter computers now in command of the countdown. T-minus 15, 14, 13, 12, 11, 10. We have a go for main engine start. 6, 5. We have main engine start. 3, 2, 1, 0. We have solid rocket booster ignition and liftoff of Challenger and the 10th Space Shuttle flight. The shuttle has cleared the tower.
Tower, switching over. Houston now controlling. Roll maneuver confirmed. 15 seconds. Good roll confirmed by mission control. 20 seconds. 25 seconds preparing to throttle down. 75% on main engines. 30 seconds. 1. Velocity 700 feet per second. Throttling down 73% confirmed as the vehicle prepares to pass through the maximum aerodynamic pressure. 52 seconds. Velocity 1100 feet per second. Downrange distance 2 nautical miles. Altitude 4.7. Back up to 100%. 3 engines down, 100%. Challenger Houston, your go at throttle up. All right, there, Houston. Challenger and crew, give them a go at throttle up. 1 minute, 23 seconds, velocity 2,300 feet per second.
After 18 years, Bruce McCandless finally earns his golden pin, and he does so alone, seated a floor below the rest of his crew, in the shuttle's middeck. The crew float free from their seats and look out of the shuttle's windows at our beautiful Earth, almost 200 miles or 300 kilometers below them. For all the mysterious wonders, splendors, and grandeur of space, this is the only one we can call our own. The only home we've got. A blue pearl in the vast abyss. And everywhere you care to glance exists the chaotic equilibrium of life. What do you see when you look at our planet?
The minutiae of being weightless were things that I already expected. You learn that right side up is the orientation where you can read the lettering on the instrument panel correctly, and other than that, it doesn't make any difference. You very rapidly learn that to go from the upper deck to the lower deck, you just sort of dive head first down through the hatch.
This is Mission Control, and we can see the sun shield on the Palapa satellite closing over to protect that satellite's delicate electronics and other parts from the direct radiation of the sun prior to the time that it will be opened again for the deployment of that satellite, which will come about a day or so into the flight. The West Star there in the foreground, the sun shield is still open on that satellite, and I'm sure they'll be closing that one shortly. That will be the first one which will be deployed, and that is later today.
Challenger carries a variety of onboard experiments common in the days of the early shuttle. The monodisperse latex reactor, or MLR, designed to manufacture tiny, identically sized latex beads in the microgravity environment, believed to have potential medical and industrial research applications. ACES, or the Acoustic Containerless Experiment System, is a materials processing furnace. The Isoelectric Focusing Experiment, or IEF, evaluating the effects of electroosmosis on an array of 8 columns of electrolyte as DC power is applied. These are just some of a litany of other experiments located both inside the crew compartment and outside in the payload bay, such as a Cinema 360 camera designed to capture sequences for planetarium viewing, and other experiments located in so-called getaway special canisters. Some of these experiments stay on the shuttle for the duration of the mission, gathering data or undergoing a physical change to be examined upon the vehicle's return to Earth. Others, however, pop open and deploy out into space, the 1980s equivalent of a CubeSat. All of these missions contain a large enough variety of ride-sharing experiments and payloads that going forward, only the ones with major relevance to the mission's primary objective will be mentioned. Located in Challenger's payload bay, alongside the 2 communication satellites Westar 6 and Palapa B2, is the Shuttle Pallet Satellite, or SPAS. This modular, reconfigurable frame, on which experiments and instruments can be mounted, is designed to be grappled by the shuttle's robotic arm and extended out into space. In some cases, it can even be released for periods of time, but it is designed to return to Earth with the shuttle itself. On this flight, the SPAS platform hosts simulated electronics boxes, similar to what would be found on Solar Max, and trunnion pins designed to simulate the attachment points found on the satellite. McCandless and Stewart, with their MMUs, will acquire a device called a T-pad, or Trunnion Pin Acquisition Device, a large, female adapter they will wear on their chest, enabling them to physically attach themselves to the trunnion pin in what will be the first ever human-to-satellite docking achieved in space. SPA's O1A also includes both film and television cameras to capture the momentous spacewalk that lay ahead. The Shuttle pallet satellite was manufactured by West German aerospace firm Messerschmitt Bölkow Blohm, and also carries several experiments called the Materialwissenschaftliche Autonome Experimente unter Schwerelosigkeit, or MAUS 1 and 2. Things such as new magnetic alloys and friction loss experiments. Like the orbiter itself, the Shuttle pallet satellite is nothing if not a smorgasbord of payloads. Challenger approaches its first major hurdle, the deployment of the 2 onboard commercial satellites. This very kind of satellite has been deployed successfully before on STS-5. The crew expects no major hiccups.
Data verifies that the sunshield sequence is commenced. And the sunshield's now open, exposing the Westar satellite.
That's affirmative, Houston. We got those on at 25 minutes.
We copy that.
Very both restraints are out, and we're staying on standing and progress.
Copy that, thanks.
Dr. McNair affirms that the restraints have been removed and the spin-up is in progress. RPM's now 31 RPM and climbing to 40, 41, 45. At 25 seconds before deployment, Dr. McNair will perform what's termed an Item 9 execute, which will be the final command sent to the satellite before deployment.
Bingo, very good. Okay. Westar deployed, we'll be back with a report in a few minutes. Dave, Bob, H-Pan Heaters, Auto, talk back gray. Talk back is gray. Deploy 3 arms off, talk back bobber bowl. 3 arms off, talk back is bobber bowl. Okay?
45 minutes after a seemingly successful deployment, the first satellite's payload kick motor, now faced in a posigrade direction, lights up, and only a few seconds later, fizzles out. This is how fine the line is between success and failure in space. One brief moment, and history is forever altered. NASA delays the deployment of the second satellite. It is of the same design and uses the same Morton Thiokol manufactured payload assist motor as just failed on Westar 6. Engineers on the ground agonize over whether or not to deploy it, potentially losing 2 satellites into operationally useless elliptical orbits on just one mission.
Oh, we got a great picture. Sounds like looks like it's a great place to go running.
Yeah, Bob, First Army officer in space, likes to do a lot of jogging and all that, so Bob is jogging on the treadmill. Ron McNair is going to take some movies of him. He has the Cinema 360 camera. Ron is, very professional in his job of movie making. We call him Cecil B. McNair. Anyway, I think Ron is, not pointing right at Bob because that's such a wide field of view lens that it actually takes in about half of the room. Houston, Challenger.
Challenger, Houston.
Okay, Mary, we've reached the point where I'm ready for the RF link activation, and I'm holding for your call.
We'll check on it for you.
We're just coming into the daylight now and starting to get a good view of the Earth with our TV cameras.
Looking at the coastline of Baja California.
With the naked eye, we can see some fields straight down, green squares. Not too much of that down there since it's a fairly dry area, though.
Should be crossing the Mexican coastline here shortly in the vicinity of Los Mochis.
And Mary, we see a contrail down below us. Matter of fact, I see 2 or 3 of them. Bruce is going to try to zoom in on one of them, an airplane flying a little bit below us there.
Roger that.
On the third day, Challenger prepares to release a major payload, known as the Integrated Rendezvous Target, or IRT. This is a tungsten-ballasted, nitrogen-inflated Mylar balloon. The IRT balloon is painted white with a small infrared black patch on one of its 24 gores. The idea is to gather CCTV infrared laser data and on-orbit radar tracking to help prove out and mature the shuttle's orbital rendezvous hardware.
Mission control, the balloon was just jettisoned from the payload bay. And the balloon now being shown from the Alpha camera, not quite in focus. The balloon should be inflated by now, but we're unable.
Challenger, Houston, if you could tell us the IRT status, we can't see it on the TV downlink.
Hey, John, it deployed, and it went out rotating with a very slight coning angle. Appears to me that it makes about 1 rotation every 11 or 12 seconds.
Roger that. And what is its current inflation status, Vance?
That's what I'm holding off on. It does not look to me like it's inflated yet.
Roger, understand.
Does not appear that the staves were fired.
Roger, understand, Vance.
Shortly after deployment, the balloon's canister failed to pop open, and it burst when inflated. As it turns out, an improper crimping tool was used to assemble the lanyard required to trigger the pyrotechnic separation of the balloon's canister. It was simply bad quality control and a poor omen of things to come. Nonetheless, the crew managed to track the crippled piece of kit out to over 100 kilometers away. Working in conjunction with the shuttle's onboard star trackers, the testing and calibration of the rendezvous data system is crucial if NASA hopes to live up to its orbital construction aspirations for the STS. But with one satellite a bust and the IRT a partial failure, the 8-day mission of STS-41B was off to a pretty rocky start. Flight Day 4. With the go-ahead given by the Indonesians, NASA commits to deploying Palapa B2 in the hope that it won't suffer the same failure as its twin, Westar 6.
Good spin currents. There she goes. We have a deploy.
I guess.
Okay, Ron, ace PAM heaters to auto.
Here's on auto.
Deploy pre-arm off.
Cassie, motor 1, currents, closing the sun shields.
Houston Challenger, you're seeing the PKM motor now.
Roger.
A hope that, as it would turn out, was in vain. Exactly the same failure strands the satellite in exactly the same awkward elliptical orbit. Shuttle Flight 10 desperately needed a win, and it was down to the climactic spacewalk and test of the MMU. The crew lowers their shuttle's cabin pressure a day before the EVA, reducing the amount of time McCandless and Stewart need to pre-breathe oxygen prior to suiting up and going outside. This was only the second spacewalk of the shuttle program, and it would be the first ever in zero-G without a tethered connection to the vehicle. Flight Day 5. This was it. With McNair operating the robotic arm, Brand flying the orbiter, and Gibson snapping photos, McCandless and Stewart prepare to make history. McCandless underestimates the liquid cooling power of the modern spacesuit, and he has to shut it off once his teeth start chattering. NASA had come a long way since overheating and visor fogging. A long and arduous road since 1966.
And we're ready to go out.
Okay, got our cameras on you.
Everything looks nice and new in this big water tank in the sky.
We got a pretty good view of you here on TV, Bruce. How do you like it out there?
Nice. That worked like a jewel. Yeah, I've already read you the nitrogen pressures. And the cross feed valves are closed. If you would, sir.
Challenger, Houston, with you at Hawaii for 8 minutes.
Well, that may have been one small step for Neil, but it's a heck of a big leap for me.
Roger, copy that, Rick.
Okay, Bruce, we see you airport.
Bruce McCandless preparing to make his 150-foot sojourn, moving away from the orbiter out to a distance of 150 feet and then returning. And then following that, about 10 minutes later, he will go out to a distance of 300 feet.
And Bob, we're not going to pay much attention to you for a little while here while we watch Bruce go out and back.
Here's a different perspective on the orbiter.
And Bruce,
I'm trying to see what sort of landmass that is we're coming up with. Looks like Florida. It is Florida. It's the Cape.
yeah, you're on the stateside pass, Bruce.
McCandless and his manned maneuvering unit constitute a separate spacecraft of their own now.
Bruce?
This record will only stand, I guess, for the next hour or so.
Just passed over Florida and Cuba.
Although I guess to break it, Robert is going to have to go 10% faster.
I think I got enough to tell the thing.
After 18 long years, Bruce McCandless becomes an instant NASA icon. The subject of one of the most famous photographs ever taken in the annals of American history.
It was very rewarding from the standpoint of having worked on its development and trained so long for it. It was also a feeling of freedom, i.e. being free of gravity and being able to fly around and assume arbitrary attitudes and positions. It really works beautifully.
The whole thing is broadcast live from a variety of television cameras recording the event in living color.
And on my first mission, well, we did lots of exciting things, but we did this really exciting thing. And that was the world's first untethered spacewalks. Now, no doubt you've seen this photo before, and you've wondered who was the gifted photographer that took this photo. Well, I'm the one that shot these photos, and the reason was because during the spacewalk, I was the only person on the crew that could work a camera. No, I was the only person on the crew that had absolutely nothing to do. So I was parked at the window, and I got this photo of Bruce McCandless just on his way out, making the world's first untethered spacewalk. You notice there's no cables, there's no tethers, no ropes tying him to us. He's flying the rocket backpack. And they used it to fly pretty far away, and equally as important to them, back to the space shuttle as well. Although, if they had, I get the question all the time, what if they ran out of fuel? What if they had an electrical malfunction? Well, we could fly Challenger over to him because we had rocket thrusters pointing every direction. So we could fly over to him and rescue him if he promises us enough money for it. I looked out the window and saw this, though, and I was jealous. I was really jealous. He's a human satellite. The Earth is going by under his feet 185 miles away at 5 miles per second. That's how fast you're moving in orbit. So I was jealous when I saw that.
McCandless returns to the shuttle, attaching the MMU and recharging its nitrogen propellant, which was being expended slightly more than expected. He swaps places with Stewart, who is installing the mobile foot restraint to the end of the robotic arm. As Stewart makes his own checkout of the MMU, McCandless, now attached to the MFR on the arm, practices satellite capture and repair techniques.
Challenger, Houston, we're back with you through TDRS and getting good TV again.
Oh, look at the sunrise. Look at the sunrise.
Okay, we copy, Jerry.
Bob, take it up and do a short checkout.
Okay.
Bob, if you look down at the Earth, you'll see Baja, California.
Astronaut Bruce McCandless working at the manipulator foot restraint.
Bruce, go ahead. Well, let's head for the stowage location.
Okay, you ready to put the MFR away?
Yeah, let's head for the barn.
Okay, I got you.
And Challenger, Houston, we're getting a real nice TV of Bruce changing out the LiO canister.
It looks like another sunny day up here.
And, Bob, can you break off the hydrazine activity temporarily?
Yes.
The astronauts use the T-pad docking device on the Shuttle pallet satellite, rehearsing the maneuvers necessary for the Solar Max rescue.
Hey, Houston, you in us? There's a duck.
Roger, Bruce, we watched it all.
The view isn't quite as exciting from this position as the upright one, but it works. Yeah, just slowly. Seems like I worked back out from the 1/4 inch position to the right on the arrow. Hey, I'm going to try just backing off with just the jaws closed and not the bolt engaged. See what happens. Well, there's your answer. Cinema 360 is still watching. Here I come. Huh?
Doc? Go ahead, watch. You going to do a flyby?
Yep.
We'll turn it back on.
after 5 hours and 55 minutes, the pair, designated AV1 and AV2, head back inside. It was an unmitigated triumph of the highest degree. Flight 10 finally had its success, and NASA had its photographs. Mankind now flies free in space. There was nothing left to hold us back. The next day, the crew takes a break, staying inside the orbiter and completing many of their minor objectives. McCandless and Stewart would go outside again the following day and rehearse docking with the Shuttle pallet satellite again, this time attached to the shuttle's robotic arm. The idea is to simulate the mild, out-of-control spin of Solar Max, with McNair rotating the spas on the end of the RMS, giving McCandless and Stewart the chance to practice the challenging grapple maneuver that will be necessary to wrangle in the massive hardware. However, as the crew checks out the various rotating and tilting joints of the robotic arm, they discover that the wrist will not move when commanded.
And this is Mission Control. We see the 50-foot-long Canadian-built remote manipulator system out of its cradle, and all the joints flexing on that. We see the wire snare system inside the end effector.
This is one of a series of compounding issues that are developing with the orbiter. One of the APU's primary gas generator cooling systems had failed earlier in the flight. The orbiter's supply water dump valve was stuck shut. They have to use the flash evaporator to dispose of excess water for the remainder of the 8-day flight. Ice buildup on an external vent would eventually lead to a chunk of ice breaking off during atmospheric entry, which would impact and slightly damage the orbiter's tile protection system. These various minor failures, which almost always happen on every spaceflight, usually just necessitate the switching to an auxiliary system. Most of the time, they don't require a change in crew behavior or an altering of the mission objectives. But without the use of the robot arm's wrist joint, they won't be able to practice the spinning docking maneuver that will be required for Solar Max. NASA decides to cancel further RMS use, and the crew simply stows it. The second spacewalk will continue, but it will be more of the same, docking with the stationary spas still secured inside the orbiter's payload bay. The pair go outside again to practice more dockings on the MMU and to conduct simulated in-orbit fuel transfers using pressurized Freon, dyed the color red. Suddenly, the mobile foot restraint begins floating loose, drifting away from the astronauts and the shuttle.
Hey guys, there goes a foot restraint into orbit.
Well, we can go get it. Houston Challenger.
Go ahead, Challenger.
Houston Challenger. We lost a foot restraint. It's starting to float out. We can go get it if you wish. The orbiter.
Yeah, why don't you?
Roger, we see it. How much gas does Bob have?
No, the orbiter.
Okay, your
They
call.
have the orbiter go get it.
Stand by.
I'm going to go get it.
Not to be upstaged by an accident, Commander Brand fires the shuttle's reaction control system thrusters, positioning McCandless in the right spot to retrieve it.
Looked like it pulled right out. I was going down to work on the secondary T-pad, having completed the primary on the control box, and it just blew off.
Roger, copy that. It was my recollection that we had a tether on that foot restraint.
Oh, we took it off, Joe, to use it. Up at the end of my tether, Vance, you're going to have to put in some -X.
Astronaut Bruce McCandless along the starboard slide wire, moving back to pick up the free-floating foot restraint.
Beautiful job, sir.
Okay, and at least it won't be re-entering in a few days.
I hope it'll be re-entering in a few days. The rest of us are planning to.
Yeah, it won't be re-entering separately.
There you go.
Commander Vance Brand maneuvered the orbiter.
Very Challenger.
Go ahead, Vance.
Okay, we thought it might get away from us, and so we went and got it, as you noticed. And I guess the procedure works okay to go get it, to go get things that get lost, which we happen to have in our procedures.
Roger that, Vance. We verified a procedure we didn't expect to use, and you got some prox ops operations in that we missed earlier.
The big thing to remember in that procedure is when you change from the upper window to the aft window, to be able to be sure and throw the descent switch at the same time.
Roger, copy that. There's always a gotcha in everything.
A small but important demonstration of the shuttle's precision and the ability of a well-trained shuttle crew to improvise, react, and solve problems on the fly. During this spacewalk, the pair receive a phone call from the President of the United States. As Reagan talks, McCandless realizes his MMU is almost out of fuel. He quietly switches it off and hopes that Brand doesn't fire any more thrusters.
Challenger Houston, the President of the United States.
Commander Brand, I'd like to say a good morning to you and your crew. I'm talking to you from California. I don't know exactly where you are. I know you're up there someplace. But you're all doing a fine job on this historic mission. And I'd like to say hello to Bruce McCandless and Bob Stewart for sending us this spectacular television coverage of man's historic walk in space. Let me ask you, what's it like to work out there unattached to the shuttle and maneuvering freely in space?
Well, we've had a great deal of training, sir, so it feels quite comfortable. The view is simply spectacular and panoramic, and we believe that maneuvering units, first time working unattached, we're literally opening a new frontier in what man can do in space, and we'll be paving the way for many important operations on the coming space station, sir.
Well, that is just great. You've really opened a new era for the world in space with this mission. You've shown both our commercial partners and our foreign partners who play an important role in this and other missions to come that man does have the tools to work effectively in space. Well, now, could I ask, how are the experiments on board the shuttle working out? I understand that you have one dealing with arthritis and other experiments on board that may lead to advances in manufacturing and various kinds of material processing.
Sir, Mr. President, the experiments are working out very well. We're very pleased with the results we're seeing, and there's a lot of promise being demonstrated in all the areas you just mentioned, and we look forward to getting them back on the ground and analyze and make some good use of these results.
Well, let me again congratulate all of you on board the Space Shuttle Challenger. You're doing a fine job. Your commitment and courage on this historic flight, I think, are an inspiration to all of us. And I know that you have things to do, and much more important than getting a telephone call from Earth. So let me just say to you, have a safe journey home, and God bless you all.
After a little over 6 hours, McCandless and Stewart wrap up EVA-2, their primary mission now at an end. A major PR success for NASA. The MMU, a piece of hardware long relegated to the back rooms of the space program, is now its darling child. One amusing minor design flaw is that the MMU's thrusters are scattered around its center of mass, failing to account for the presence of the astronaut wearing it. As a result, translatory bursts to move forwards, backwards, left and right, up and down would inevitably impart some rotational momentum as well, which would have to be counteracted by yet more thruster bursts. In short, it wasn't very fuel efficient, compounded by the fact that its fuel was simply pressurized gas. It was weak as well, but it may just be enough to enable the kind of rescue needed for Solar Max. Flight 11, which would also be flown by Challenger, would find out for sure. But first, Challenger would have to land, for the very first time in Florida.
Challenger, Houston is with you at Mala.
Roger, Houston, and we're passing Block 11. Doing great. Beautiful show.
Roger that, and be advised, the current Cape weather is clear, 30 miles visibility.
Super. Hey, thank John for getting us that kind of weather. John Young.
Roger that.
Airspeed 256 knots. Speed brakes deployed. Velocity is now subsonic at Mach 0.9. 25 miles from the runway, altitude 47,000 feet. 11 miles range, 10 miles from the end of the runway. Airspeed 256 knots, altitude 17,000 feet. Gear down. Touchdown. Space Shuttle's first Florida land. Mission shuttle last 7 days, 23 hours. Nose gear down. Touchdown at 190 knots.
NASA was eager to test the new Shuttle landing facility, a 15,000-foot runway that, ironically enough, was much shorter than those at Edwards Air Force Base in California. It was also surrounded by what astronauts came to call the alligator moat. Too little energy, or too much, could lead to disastrous consequences in an area known for its intense tropical weather. However, it was also located right at the same facility that the shuttle launched from, the Kennedy Space Center. Being able to land the shuttle right there and tow it directly into the orbiter processing facility would drastically reduce the turnaround time and costs, eliminating the need to fly it back from California on the back of a Boeing 747.
Has egress air seats now leaving the ship. Vance Branford, Steve Gibson, Bob Stewart, Ron McNair, and Bruce McCandless.
With Mission 41B complete, Challenger enters the OPF, beginning a rapid turnaround and immediate preparation for STS-41C, Space Shuttle Flight 11. This is indeed, in some ways, the Apollo 11 of the Space Shuttle program. The very first attempt to rescue a stranded satellite in space, effect repairs and release, redeeming a doomed mission, and extending the life of an observatory in space, ultimately saving the American taxpayer untold millions by averting a scientific flop. It would be the ultimate test of the shuttle's capabilities, as well as those of its crew. Challenger's next mission is just under 2 months ahead, set for April. Its 5-man crew rigorously trained for their flight. The commander of Mission 41 Charlie is none other than Mr. Shuttle himself, Robert Crippen. Making his third flight into space, He flew on the first shuttle mission ever, STS-1, with John Young 3 years ago. He also flew on STS-7. His reputation is solid gold, and he's the perfect man for the job. He was scheduled for this flight back when it was still known as STS-13, even though it ended up flying as the 11th shuttle mission and designated 41C due to the new naming convention already mentioned. A lot of early shuttle missions are moved around, delayed, and manifested multiple times. The original schedule had such an aggressive launch cadence that they were predicting over 20 flights by 1982. STS-13 could mean several different missions depending on when it was you were researching. Not only will Crippen and his crew rescue Solar Max, but they'll also be deploying a massive passive satellite called LDEF, or Long Duration Exposure Facility. Originally called the Meteoroid and Exposure Module, LDEF is a payload long in the making. Its incredible size makes Shuttle the only vehicle capable of carrying it into orbit. LDEF is known as a, quote, big dumb satellite. It's nothing more than a massive 12-sided stainless steel cylindrical prism on which dozens of different kinds of materials are mounted, exposing them to the space environment. The idea is that this behemoth will be left in orbit for a period of time to be recovered by another shuttle and studied by scientists on the ground to see how a variety of materials stand up to the harsh weathering of outer space. It's one of the oldest planned shuttle payloads, getting its initial approval in 1974. It doesn't have any onboard propulsion or attitude control, instead achieving stability with gravity gradient inertial mass distribution. It is extremely important, however, that the shuttle deploy it as gingerly as possible, not impinging upon it with any RCS thruster blasts, which could cause it to wobble. There are some basic onboard electronics, including some experiments that record data on onboard magnetic tape, but otherwise it's an extremely primitive payload. Challenger will release LDEF once in orbit, and then proceed towards the stricken Solar Max. Challenger's pilot for the 41C mission is Francis Scobie, a highly accomplished test pilot with thousands of hours spent flying experimental and prototype aircraft. He's one of the best pilots NASA has, a member of the group of 1978. The third member of the crew is robotic arm operator Terry Hart, an electrical engineering specialist with 2 patents under his name, spending 10 years at the innovative Bell Labs before his selection as a NASA astronaut. Lastly, the 2 spacewalkers who will follow up on McCandless and Stewart's MMU experience. 6'4" astronaut Dr. James Van Hoften, known as Ox, and his 5'9" partner, Dr. George Nelson, known as Pinky. Crippen and his dynamite crew are among the best in their group, and that's by design. Their mission promises to be one of the most challenging yet undertaken. They christen themselves the ACE Satellite Repair Company, a reference to a social group called the ACE Moving Company, formed by some shuttle-era NASA astronauts that helped the widows of former flight test colleagues who had died in flight testing move out of their on-base housing. It's a form of gallows humor that taints many astronauts from the early shuttle era, some of whom hail from what Mike Mullane would later call planet-arrested development. It's important to acknowledge the bigger picture of the early 1980s. The culture is changing in the astronaut corps. It's no longer just fighter jocks with crew cuts competing for flights. Civilian scientists and academics, some of them black and some of them women, all of them undoubtedly accomplished, are now front and center in NASA's space program. Backroom tales of forced innuendo, questionable behavior, and sexual harassment aside, this is the most diverse group of astronauts ever assembled, and they bring with them conflicting ideas of what an astronaut should be and is entitled to. There can be no question, however, of this crew's unimpeachable qualification. They are the right people for the job, and NASA now looks to them to raise the bar.
We have a go for APU start. The firing circuit for the solid rocket booster ignition and range safety destruct devices has been armed by the Ground Launch Sequencer Command. The shuttle is now on internal power. T-minus 45 seconds, just 14 seconds away from switching command of the countdown to the onboard computers. 13, 12, 11, 10. We are go for main engine start. 8, 7, 6. We have main engine start. 3, 2, 1. Solid motor ignition and liftoff. Liftoff of Challenger and the first flight to repair a satellite in space. We have cleared the tower.
Houston controlling now. Roll program initiated. Good roll. Puts the Challenger in the proper attitude for its flight downrange. Standing by the throttle down for max Q. Throttle's down to 67% as Challenger goes through its period of maximum dynamic pressure. Standing by the throttle back up as Challenger passes to the speed of sound. Velocity. All throttles back.
And go and throttle up.
All throttles back up to 104% of rated thrust.
John, you guys still down there?
Roger that, Crip. Still with you.
Okay. Well, the view from here is as fantastic as ever.
Roger that, Crip. You guys really look good going up the hill this morning.
Yeah, it's a nice day for a launch. And we could just handle that kind of stuff on about 1 entry.
Roger that.
41C executes a so-called direct ascent launch profile. Until now, the shuttle's main engines had just barely gotten 99% of the way there, and the orbiter then used its 2 smaller OMS engines, or orbital maneuvering system, to cross the finish line into low Earth orbit. This time, however, OMS fuel is preserved as the main engines do the entire job, and push the orbiter and the massive external fuel tank, which later re-entered due to atmospheric drag over Hawaii, into orbit. It was just 55 days since Challenger last flew into space. The shuttle enters a 252 by 137 nautical mile elliptical orbit. Over the course of the next 2 days, further maneuvers will be made with the OMS engines as the orbiter catches up to a rendezvous with solar max. The crew lowers the cabin pressure to 10.2 psi in preparation for the EVA. However, a minor procedural error made by the crew during the pre-breathing protocol necessitates that they start over. Crippen activates the retention latches, and Hart grapples the massive LDEF, gently maneuvering the beast out of the shuttle's payload bay.
As the Challenger crew continues checkout of the remote manipulator arm and berthing and unberthing and rebirthing the LDEF payload, this 21,000-pound structure is 14 by 30 feet and contains some 86 trays of various types of materials in materials and structures, power and propulsion, science and electronics and optics fields or disciplines, representing a total of 57 individual experiments that are being managed by 194 principal investigators around the country and around the world, actually.
Challenger Houston through Hawaii for 10 minutes. We're getting pictures, and I think I copied deployed and backing away.
It's going away in air chair, and it was as steady as a rocket motor and just about as big.
Roger that. Thank you very much. All the Langley folks are cheering downstairs, and we've got our LDEF buttons on up here.
They gingerly let go. LDEF is now flying free in space. The shuttle has the capability to operate its up-down translation thrusters, or in other words, the Z-axis, in a completely separate, offset configuration, blowing plumes out to the sides rather than direct. It's less fuel efficient, but it also enables the shuttle to operate in extreme proximity to a delicate object, such as a space station with long and flimsy solar panels, without inducing a physical interaction with the high-velocity gas exhaust. Challenger pulls away from LDEF, its scientific mission having now begun. One day, we would come back.
Challenger Houston, TJ, we'd like a verification of the deploy time, please.
It was on time.
Copy, thank you.
We got a sweet lock on the radar at 70 feet.
Roger, that sounds real good to us.
Challenger carries, once again, a variety of onboard experiments. One of the more interesting ones on this flight is what NASA calls the bee enclosure module. A student experiment, this habitat box houses 3,300 honeybees, and the crew observes their behavior in the microgravity environment, whether for reasons of scientific curiosity or simply to double-check on the container's structural integrity. This experiment, ironically enough, is sponsored by Honeywell. Solar Max is remotely powered down, what fuses did still respond, to ensure that it would not try to resist any attitude changes incurred by the upcoming recovery. The crew spots it at a distance of 156 nautical miles. Ox and Pinky don their spacesuits. The orbiter closes in.
Challenger Houston, Solar Max is ready for rendezvous.
All right, so are we.
Mission Control Houston, rendezvous radar shows Solar Max to be 17.3 nautical miles forward of the orbiter Challenger.
And Houston Challenger, be advised we're configuring for EVA at this time.
The spacewalkers exit the internal airlock into the payload bay. Nelson mounts the MMU, and Van Hoften helps him position the T-pad docking device on his chest. Hart stands by on the robotic arm, ready to assist. This was it.
Take your time.
Challenger Houston, the Solar Max is ready for capture.
Roger, we catch. Copy, ready for capture.
Range 300 feet, closing at 0.35 feet per second. EVA crewmen going through the MMU activation and checkout, removing the launch bolts.
This is a pretty good flying machine you got here.
Roger, I can see the smile on your face from here.
I'll take you, Jan. Nice about this is I can lay on my back. Wow, look at that. Boom. Hey, that is neat looking.
Nelson slowly flies off into space, ready to pluck a satellite out of the sky.
Have a good one, mate. Thanks, Alex. You needed that. I go, 1 potato, 2 potato.
Nelson on his way at 1 hour and 2 minutes.
Hope you're moving faster than I am. How are you doing, okay? Satellite looks in excellent condition. Doesn't work. Yeah, Jaws didn't fire that time. And the Jaws didn't fire. Okay, we can try again. Thank you, read us.
Pardon me, I don't know if he's docked yet or not.
The Jaws didn't fire.
EVA, Jaws didn't fire. Do you have a...
They did again, they didn't fire again.
Okay.
Didn't fire again. Apparently the trunnion pin adapter did not latch properly. No joy there.
Try as he might, the T-pad would not make a firm connection to Solar Max. A small metal grommet on the trunnion pin, designed to hold a thermal blanket in place, was the obstruction, something the satellite manufacturer failed to note in its blueprints provided to NASA. The T-pad, and any hope of a mechanical capture by an astronaut of Solar Max, was a dud. Dead in its tracks, thanks to 1.5 centimeters of mechanical clearance. A small metal grommet holding up a $50 million rescue. This is how thin the line is between success and failure in space.
You're going to have to hold on to it both hands, I imagine. You've started that rotation about to your left now, and we really need to stop that to do a rotating grapple. Is there any way that you think you can do it with your hands if you can't get a grab hold of it? Yeah. Stop it. No, there's terrible. Think you read us? Yeah, I do. Okay, great. About it, Trip. I don't know if I'm going to have enough gas to do that. Oh, what you got left? What you got left? Yeah, 1,200 on one side. Yeah, 1,200 on both sides. I guess so. Okay, come on back in, thanks. Which way is it moving now?
Nelson tries in vain to grab the satellite with his hands, but he only ends up making the situation worse when it starts wobbling about its long axis. Now it wasn't just spinning, it was tumbling too. Running out of fuel, he's forced to retreat back to Challenger. Once he's there, Crippen closes in. He's not ready to give up just yet, and the crew entertain notions of snatching it quickly with the robotic arm. However, the combined motion is too much. There's a chance they could damage the arm itself if it collides with the spinning satellite, not to mention the danger to the orbiter. Nelson and Van Hoften terminate their first EVA after just under 3 hours. The MMU's big shot, through no fault of its own, a bust. Challenger pulls away, intending to make a re-rendezvous and grapple attempt. However, as the crew prepares to sleep, Mission Control is abuzz with activity. They decide to postpone for 24 hours, adding a day to the flight, and giving Goddard engineers the chance to stabilize it from the ground with whatever means they have available. Miraculously, they break the rotation down to just 0.5 degree per second. It may now be slow enough for a direct shot on the robotic arm. It would be close, and it would be down to the skill of Terry Hart. Flight Day 5. Challenger closes in on Solar Max with everything on the line. Mission Control can do nothing but watch. It's up to the humans who fly into space to save one of the robots that threaten to replace them.
Challenger Houston will be handing over to Tidris in less than 2 minutes. Solar Max is ready for capture. Their coning angle is less than or equal to 15 degrees this time. Rotational rate is approximately 1/2 degree per second. And we would like UHF re-enable, please.
100 feet, closing at 0.25.
Challenger Houston, 1.5 minutes till LS Tidris. Solar Max is starting to feel a bit of plume impingement. We know we're in good hands and use nice soft gloves.
Do our best.
Remote arm is now in motion. We should have confirmation on whether the first grapple attempt was indeed successful.
Challenger Houston standing by through Yargity.
Okay, we've got it, and we're in the process of putting in the FSF. Outstanding. Forward
forward, RCS, propeller remaining is 41 Charlie.
Roger, copy that.
Hart manages it on the first try. Hart maneuvers the satellite onto a restraint platform known as the Flight Service Structure, or FSS. This is where Van Hoften and Nelson can easily reach it and implement repairs. Flight Day 6. Nelson and Van Hoften's repair has been salvaged, and they suit up to go outside a second time to fix Solar Max.
Hey, capture away, sir.
Okay, end effector going to manual mark. Capturing mark.
Okay, you got it?
Close and capture. Let me know when you're ready to rigidize.
Hey, rigidize.
Okay, rigidizing mark. Mission Control, Houston, Van Hoften now in the manipulator foot restraint.
Drag me up a little bit more and a little bit more towards the satellite.
Got plenty of room towards the satellite, TJ.
Nelson and Van Hoften, utilizing the mobile foot restraint at the end of the robotic arm, with Hart at the controls, replaced the attitude control module and defective electronics in the coronagraph polarimeter instrument.
I got 1, 2. Hey, looks good. Hey, it's on there. And off she comes. Watch that little wheel. Hey, it's on 0.5. Open. Okay, volume is loose. Coming out of the unlock. Sit.
Mission Control, Houston, it looks as if we've gone LOS Tejas. That last pass-through Tejas we listened in as the astronauts worked on the attitude control system. The EVA is working along very well. They've pulled out the old ACS module, are putting that down on the flight support structure and endeavoring to take the new one and place it in the Solar Max.
Through the night, the Payload Operations Control Center has continued to check out the Solar Max satellite to verify the repairs made by the astronauts yesterday. Ground controllers have completed checkout of the new attitude control system and found it in excellent working order. They have also completed deployment of the satellite's high-gain antenna, which will be used to communicate through the tracking and data relay satellite once the Solar Max resumes operational life. The antenna was gimbaled in single and dual axes successfully and presented no problems in deployment, though it had not been moved previously since the launch of Solar Max in 1980. Additionally, the Payload Operations Control Center has checked out the repaired main electronics box for the coronagraph polarimeter instrument. The Solar Max satellite is now ready to be released from the shuttle's robot arm upon the command of the shuttle crew, now expected at about 4:30 Eastern Standard Time this morning.
The repairs are ultimately a success, and Solar Max would go on to study the Sun for another 5 years, providing a boon of data that is substantially more advanced than what was captured on Skylab, whose Apollo telescopes recorded solar activity in 1973. Solar Max's onboard instruments can record information embedded inside powerful flares that would simply wash out the instruments on Skylab. The satellite observed such things as neutrons emitted by a solar flare, produced when beams of protons strike the solar photosphere, the so-called visible surface of our parent star. We've known about these protons for some time, but their charge forces them to spiral around in space, following magnetic field lines between the Sun and the Earth. The presence of the neutrons, however, which travel in a straight line, allows scientists to infer the energy of their proton counterparts at the moment of their production. It was thought that these protons took almost half an hour to accelerate to their incredible velocity. That acceleration instead takes only 2 seconds, thanks to an electric potential generated by the solar flare of some 25 million volts. Our star is a powerful particle accelerator. Other instruments, such as the hard X-ray imaging spectrometer, help us map the hidden shape of solar flares, utilizing new wavelengths of light. Studying the Sun in X-ray shows us that flares are compressed magnetic loops of stellar material colliding with each other like 2 live wires being brought together exploding the local temperature to more than 100 million degrees in less than a minute. Solar Max measures the plasma density, tracks sunspots and flares, and gives us an insight into the interior of our home star until it ultimately re-enters the Earth's atmosphere in 1989, its scientific mission more than a resounding success, thanks to the humans who came along and fixed it.
Challenger, the President of the United States.
Well, once again, I'm calling to congratulate you and the rest of the crew aboard the Challenger there on an historic mission. The retrieval of the Solar Max satellite this morning was just great, and you and the crew demonstrated once again just how versatile the space shuttle is and what we can accomplish by having a team in space and on the ground. I know you'll agree that those folks at the Goddard Space Flight Center did a fantastic job maneuvering the satellite for you. I guess you made one long reach for man this morning when you snapped that satellite with the 50-foot robot arm. George and Jim, you've done fine work as well. The pictures sent back of you working in space are spectacular. They're also a little scary for those of us that are sitting comfortably anchored to the Earth. But, Bob, I understand that satellite you have on board would cost us about $200 million to build at today's prices. So, if you can't fix it up there, would you mind bringing it back?
Challenger was originally going to boost Solar Max's orbit by 15 nautical miles, but the extra propellant used up for 2 rendezvous maneuvers means it is left in a 270 nautical mile circular orbit. Unsatisfactory weather at the Kennedy Space Center waves off a landing attempt there, and Challenger instead heads for Edwards Air Force Base on Friday, April 13th.
Challenger Houston looking good on final, winds are calm.
I got a wind.
The MMU had worked flawlessly on 41C, but the public perception very much became that an astronaut on an MMU had failed to accomplish a mission objective that the robotic arm later could. It was a pretty bad turn of events for the MMU, which seemed to flop on its first major test of utility. However, NASA personnel still believe that the MMU can provide an extra measure of control in the retrieval process of future satellite recovery operations. And planning immediately begins for a new mission in November to recover the 2 satellites that had fizzled out on STS-41B. NASA would have to quickly design a new capture mechanism. The MMU had yet to prove its real worth, and NASA needed to showcase its capability, lest its funding get cut by Congress. This video is sponsored by the people who support this channel through avenues of voluntary funding such as Patreon or PayPal. You are witnessing over $3,000 of new footage scans, and no part of this film is used for commercial gain. If you enjoy these films, please consider contributing. For just $5 a month, you can enjoy access to raw footage, primary source documentation, and exclusive updates into upcoming films, as well as early viewing. For those of you who do support this channel financially, thank you so much. 100% of proceeds are reinvested in getting more footage and bringing more of our beautiful, shared history of space exploration back into cultural relevance. A more exciting kind of test flight is ready to roll towards the pad. It's not every day you get to fly a brand new space shuttle for the very first time. OV-103, the Orbiter Discovery. NASA got her delivered in 1983. Now, as April turns to May 1984, she's gearing up for her maiden voyage in June. Discovery is a special ship, several thousand pounds lighter than both Challenger and Columbia. This orbiter also sports a unique thermal protection system design that differs from the other. Discovery was built to unique specifications outlined by the U.S. Air Force. Namely, it needs to be able to re-enter from a polar orbit, which would necessitate slightly higher G-loads and orbiter skin temperatures. Discovery is to be used for classified DoD missions, largely in the realm of deploying and recovering spy satellites. This is far and away an intrusion of national security objectives into NASA's civilian mission, but it's a key part of the Space Shuttle's funding. The Shuttle competes with traditional rocket families such as Delta and Titan, and once Slick 6 is fully operational at Vandenberg, Discovery will be the vehicle of choice for the U.S. Air Force Space Command, now known as the Space Force. It is in some ways the military's shuttle, but until Vandenberg is ready, Discovery will fulfill missions just like any other orbiter, and its first one is a doozy. STS-41D will see the deployment of a new kind of satellite, one much bigger than what we've seen already. A spin-stabilized cylindrical communications satellite also built by Hughes. This is a design known as SYNCOM-4, or Synchronous Communications Model 4, falling under a new program called LESAT, or Leased Satellite. These are the first platforms designed specifically to be launched by a space shuttle, and they provide worldwide communications to the U.S. military and American overseas allies, such as countries within NATO. Another major payload is a gigantic expandable solar panel for the Office of Aeronautics and Space Technology, appropriately named OAST-1. This prototype is a new class of very lightweight, flexible arrays designed for multiple deployments and retractions. The low-frequency structure, designed to dampen out vibrations, is a key part of the upcoming Space Station Freedom, a proposed multi-module orbital habitat to be constructed by space shuttles. At launch, it occupies a box only 7 inches or just under 18 centimeters deep. When fully deployed, the mast extends over 100 feet or 30 meters into space. Discovery will also carry the large format camera, a true optical monster, the likes of which have never been flown into space. On Apollo, the Command and Service Module carried on the J missions of 15, 16, and 17 a camera system derived from the U-2 and SR-71 spy plane programs, taking massive strip chart orbital photographs of the lunar surface on mind-boggling 5-inch wide or 127mm film. By comparison, IMAX film, which continues to be the industry standard even today, occupies the 65 to 70mm range. Well, the LFC blasts both of these out of the water, sporting a film format of 23 by 46 centimeters, not millimeters, centimeters. 9 by 18 inches. This camera will provide Earth surface photography, resolving objects down to just 14 meters across on the surface. The 22nd of June, 1984 approaches, and Discovery, an untried shuttle, gets ready to stretch its wings for the very first time. After an 18-second firing of the main engines on June 2nd, known as a flight readiness firing, engineers discover a thermal shield in main engine number 1's combustion chamber had become debonded. It's replaced, and the launch is pushed back to June 25th. The first launch attempt is scrubbed at the T-9-minute hold point due to a failure of one of the backup general-purpose computers. NASA orders a 24-hour recycle and tries again on June 26. The main engine start of a space shuttle occurs at T-minus 6.6 seconds. All three engines are lit in a staggered order, and they have only 4 seconds to come up to thrust and stabilize before the solid rocket boosters are ignited. That's all the time the computer gets to sample the engine output and make a clear determination of go or abort. Never before in the shuttle's history has a mission been aborted once the ignition sequence has begun. Never before until today.
10. We have a go for main engine start. 7, 6, 5. We have main engine start. We have a cutoff.
NTD, we have an RSL abort.
We have an abort by the onboard computers of the orbiter Discovery.
EPD, verify the big monitor SRM and ignition is safe. EPD, verify that. Okay. Brake. TLS shows engine 1 not shut down. Okay, PLT. CSME, verify engine 1. Shut down engine 1. OTC, we do not show engine start on 1. OTC, CSME, I can verify push shut down and engine 1. No, we show start prep engine 1. Okay, are all engines shut down? Can you verify that?
On board, the crew of 6 wait helplessly in their seats. Commander Henry Hartsfield, veteran of STS-4, works with pilot Michael Coates, overseeing the orbiter as it's brought back from the brink of flight. Joining them on the flight deck are mission specialists Mike Mullane and Dr. Stephen Hawley. Below, on the middeck, Dr. Judith Resnick, mission specialist. Alongside her is the first ever commercial payload specialist to fly into space, Charles Walker, flying for the McDonnell Douglas Company and overseeing several commercial experiments on their behalf. Hartsfield does not give the order to evacuate immediately, a so-called Mode 1 egress. He's reluctant to use the slide wire evacuation system, as it's never been tested. This decision was a fortuitous one. By the time the astronauts do exit the orbiter, they're doused with water from the pad deluge system, tripped due to an invisible hydrogen fire that could have threatened their lives had they left when the standard procedure called for it. Ground engineers would find scorched paint trailing all the way up to the crew access arm. A hydrogen fire in the vicinity of a gigantic fuel tank full of liquid hydrogen and liquid oxygen. Just before launch, the shuttle is at its most dangerous. Pulled back like a slingshot, it's standing on the edge of a chemical energy disaster. This was a rare instance of a post-ignition on-pad abort, like the one that had occurred on Gemini 6 back in 1965. As it turns out, one of the 3 main engines didn't ignite at all, thanks to a sluggish valve, contamination in a hydraulic actuator, leading to a temporary blockage in one of the 3 engines. NASA always expected some teething problems with breaking in a brand new orbiter, but no matter which way you cut it, the first RSLS abort in the shuttle program was a big deal. Not only do the crew have to scrub their launch attempt, but Discovery is going to have to be rolled all the way back, demated, and the faulty engine replaced. This puts even more pressure on the flight schedule. STS-41E, the following mission, had already been cancelled due to developmental problems with the inertial upper stage, a more powerful booster for shuttle-launched satellites. Now, thanks to the delay and rollback of 41D, NASA decides to cancel STS-41F, Discovery's second mission as well. There's just no way they can make it before the end of the fiscal year. The agency is under the gun. They've got a budget and a schedule they'd like to try and keep. It's imperative for both congressional funding and their commercial partnerships that they deliver their promised payloads on time. Therefore, an unprecedented decision is made. A last-minute remanifestation of Discovery's maiden voyage. What if NASA could take the commercial satellite payloads for the cancelled STS-41F and combined them with the payload already slated for STS-41D. Engineers on the ground open up Discovery's payload bay and get to work. STS-41F's payload includes 2 satellites of the kind we've already seen, more telecommunications platforms using the Hughes HS-376 body, which, if it isn't clear by now, is among the most popular communications satellite designs in the world. The 2 smaller satellites being added to Discovery's mission are Telstar 302 for Telesat of Canada and SBS-4 for Small Business Systems. The existing satellite, Syncom 4-1, is swapped out with an identical sister, Syncom 4-2, thanks to a misbehaving UHF relay circuit discovered after Discovery's rollback. In order to make room for the 2 extra satellites, NASA bumps the LFC camera to a later mission and removes some minor payloads, such as a getaway special canister. OAST-1, the prototype solar panel, would keep its seat, remaining on the new, remanifested 41D. It's hard to keep track, but this is the reality of the shuttle program. With so many missions slated and orbiters in the rotation, payloads are bound to get moved around. The combining of Discovery's first and second missions into one payload represents a certain economic savvy on the part of NASA, who increasingly has to be budget and schedule conscious in this new era. Government funding for civilian space exploration ain't what it used to be, and the shuttle relies on partnerships with private industry and the military. Increasingly, NASA cannot afford delays. Discovery's maiden launch is pushed back over 60 days to August 29th. Carol Bobko and his STS-41F crew are bumped to a later mission. They'll ultimately fly in 1985. Hartsfield and the 41D crew now have a new mission on their hands. Discovery's first flight is now going to be one of the heaviest. A record-breaking 41,180 pounds, or 18,681 kilograms. Not 1, but 3 satellites, a massive solar panel, and a litany of minor experiments. Its faulty engine replaced, the orbiter is restacked, re-rolled, and ready to go. Another 1-day delay occurs when a flight software issue occurs at T-minus 7 minutes. That was the 3rd strike. NASA develops a last-minute software patch, fixes the computer timing issue, and recycles 24 hours. August 30th, 1984. The crew was fed up. They were ready to light this candle. The countdown is briefly held up when a private aircraft strays into NASA's airspace. It's chased off, and the launch proceeds.
We have main engine start. 3, 2, 1. We have SRB ignition and we have liftoff. Liftoff of mission 41D, the first flight of the orbiter Discovery, and the shuttle has cleared the tower.
Mission control confirms roll maneuver. Standing by to throttle down to 65% to begin passing through the period of maximum aerodynamic pressure. Throttling down in a 2-step fashion, first 84%, then to 65%. Throttling down confirmed, 45 seconds. Altitude 3.5 nautical miles, downrange distance 2 nautical miles. Velocity 2,150 feet per second. Passing through the period of maximum aerodynamic pressure. Engines running at 65%, velocity 2,400 feet per second. Engines throttling back up. Throttling to 104%.
Houston, go and throttle up.
Discovery, roger, go and throttle up.
Coming up on 2-engine transatlantic abort capability to Dakar.
Discovery Houston, a correction on the performance call. First stage performance, low.
Okay, John, first stage performance low.
Discovery Houston, negative return.
Roger, John, negative return.
With that call up, the Discovery can no longer turn around and return to the launch site in the event of an abort.
The satellite is powered up and configured, and everything looks real good on board.
Discovery Houston, we're 1 minute to hand over to Tidris. Your go for the deploy.
Discovery, roger. Go for deploy.
This is Mission Control, Houston. We're now 3 minutes from deploy of SBS-4 and approximately 17 minutes 52 seconds from ignition for the separation maneuver.
And Houston, Discovery.
Go ahead, Discovery.
Okay, as you can see, we had a good deploy. Right on time. I've got the current attitude and rates if you're ready to copy.
Go ahead, Mike.
And payloads reports that we had...
You'll be glad to know more good news. We just had a very good nominal perigee kick motor burn.
Okay, Dick, that's real good news. We're up here celebrating.
And payloads reports that...
Again to answer tomorrow.
All of the systems people happy with the condition of the orbiter and the CENTCOM. The 3 retaining pins have been retracted. We're 30 seconds away from deploy now.
That's a big number, isn't it? Look at that. Get some shots of that.
CENTCOM's deployed, Houston.
Roger that. Good news.
All 3 satellites are deployed successfully, and their kick motors light without issue. The earlier problem that had plagued STS-41B's satellites to an early flameout had been solved. The crew extend and retract the massive solar panel, documenting its behavior in the space environment. It generates 12.5 kilowatts of electric power, and crucial thermal and structural performance data is obtained that will help NASA design solar arrays for the space stations of the future. Only minor issues affect Discovery, the most significant of which is a monitor failure, CRT-2. The crew swap it out with CRT-4. By flight day 4, NASA was inferring, based on the performance of the supply water dump system, that ice had again built up around its vents. The crew uses the robotic arm to inspect the area, and indeed discovers a large column of ice. Over the course of the next day, the crew try to shake it loose with RCS firings, and even depressurize the cabin in preparation for a contingency EVA. They use the robotic arm to try and scrape the ice off. This, combined with deliberate solar exposure on the affected area, seems to work in successfully eliminating the icy buildup.
Well, hello to Hank and both Mikes, Steve, Judy, and Charlie. Sounds like a little community of town you've got going up there. Listen, we're following your exploits, and you're doing a great job. May I ask, is Dr. Judy Resnick nearby?
Yes, sir, Mr. President.
Well, Judy, how is it your first flight? How's it going? Is it all that you hoped it would be?
It certainly is, and I couldn't have picked a better crew to be flying with, even if they are all Air Force and Navy and Army guys fighting about who's best.
Well,
Flight Day 6. Entry Day. Discovery's coming home. The crew wakes up early due to a developing oxygen leak of some 30 pounds per hour. They manage to isolate it and stop the flow of oxygen to the point of the leak, but this is a fairly sour note on Discovery's final day in space on its maiden voyage. However, it should be acknowledged that it is expected in some way or another for any spacecraft to have shakedown problems on their first flights. Discovery, like the other shuttles, has its own unique construction and personality. As Discovery touches down at Edwards Air Force Base, it loses pressure in the right main gear strut, causing the orbiter to pull slightly to the right. After the mission, the recovered solid rocket boosters used for the launch are disassembled and inspected, ready to be refurbished for a later flight. That's when Morton Thiokol engineers discover soot located beyond the inner rubber gaskets or O-rings that segment the boosters. This is the first documented case of blow-by, evidence of flame managing to penetrate these flexible joints. It would not be the last. October 1984. Challenger is back up to bat with a landmark crew. For the first time ever, 7 people will be flying into space at the same time. The STS-41G crew. On board are 5 men and 2 women. Commander, yet again, Robert Crippen. Crippen's flight on 41G, his 4th overall, will be his last. For some time now, he's been looking forward to retiring and entering the private sector. He fully intended to retire after mission 41C, but Director of Flight Ops George Abbey soon offered him a lightning turnaround command to see how quickly an astronaut could be trained and flown on another mission. Crippen will be flying into space for the 2nd time in a 6-month period. His pilot is John McBride. Mission Specialists 1 and 2 are Dr. Catherine Sullivan and Dr. Sally Ride. Ride is making her 2nd trip into space. Her first, STS-7, was also commanded by Robert Crippen. Sullivan and Mission Specialist 3, David Liestma, will conduct a spacewalk on Mission 41G to demonstrate the human operation of the Orbital Refueling System, a framework developed by the Engineering Directorate at the Johnson Space Center. This allows a shuttle to deliver over 500 pounds or 230 kilograms of hydrazine fuel to a hypothetical satellite in need of refueling. On Mission 41B, McCandless and Stewart operated a basic version of this system using colored Freon. This time around, however, the astronauts will be using the real stuff: corrosive, toxic hydrazine fuel. The 2 astronauts will connect a feed line to a simulated satellite panel, and once the spacewalk is completed, a remote command from inside the shuttle's cabin will initiate the hydrazine transfer. Refueling in orbit is a key part of the shuttle's strategy to evolve into a true toolkit, a pickup truck in space. Sullivan and Liestma will not be using an MMU for any part of their spacewalk. They will be assisted by the robotic arm, with Sally Ride at the controls. The 6th crew member is Paul Desmond Scullypower, a civilian employee of the United States Naval Undersea Warfare Center. He's flying on behalf of the U.S. Navy and will conduct oceanographic studies of such things as the propagation of extreme waves, sea ice, spiral eddies, and oil spills. Scullypower is an American citizen, but was born in Australia. Finally, the 7th member of the crew is Mark Garneau, who will be the first Canadian astronaut to fly into space. Garneau is the section head of the Communications and Electronic Warfare Center based in Ottawa, and is a naval commander. He will operate a series of experiment packages for the Canadian National Research Council, called CANX, including but not limited to new night vision cameras, solar radiation studies, atmospheric glow measurements, space adaptation syndrome investigations, and a composite materials exposure package mounted to the robotic arm that will be held out in the direction of flight for 36 hours of Challenger's mission in space. Scully Power and Garneau are payload specialists, not mission specialists, and knowing the difference is worthwhile. Although mission specialists don't occupy a specific operational role in flying the shuttle, they are trained pilots and can do so in an emergency. Payload specialists, however, are not. They are essentially scientific passengers, and this represents a significant leap forward in spaceflight. Gone are the days where every member of a spacecraft's crew have to know how to do every conceivable job on board. The routinization of space operations on the shuttle allow for a significantly higher degree of crew specialization. It's worth repeating, too, that every shuttle mission contains multiple pages of experiments and investigations, both in the payload bay and exposed to the space environment, and also inside the crew cabin. Each shuttle flight can be thought of as a sampler platter of science, a cross-section of dozens of disciplines, all converging on one thing: a ride-share into space aboard a vehicle so large and powerful that it would be a waste not to. Many experiments have flown over and over again. Many payloads are student-led. Some are even artistic in nature. Challenger carries with it the first ever attempt to create new art in space. Using vacuum deposition techniques, 8 glass spheres will be coated with thin layers of precious metals to create what the artist, Joseph McShane of Prescott, Arizona, calls lustrous space sculptures. As on missions 41C and 41D, the crew are trained in the operation of ultra-high-quality IMAX film cameras, capturing stunning video sequences in great detail for the production of educational films. Challenger sports a large radar in its payload bay called SIR, or Shuttle Imaging Radar. Developed for the Office of Space and Terrestrial Applications, SIR is a powerful radar platform that will remotely probe the Earth's surface, penetrating the oceans and topsoil, allowing for a macroscopic scale study of the Earth's subsurface. A new perspective gained from a new plateau of observation. SIR has flown once before on STS-2. It discovered ancient river channels in Egypt and Sudan under the sands that are possibly 40 million years old. This time, the radar is able to tilt, providing an oblique view to large swaths of the Earth's surface. It will be used to map tectonic plate boundaries, meteor impact craters, vegetation, crop monitoring, and tropical deforestation. It will even be used to hunt for evidence of early human activity, searching for ancient Nordic ruins in southern Sweden underneath solid limestone. Finally, STS-41G will deploy a scientific satellite called ERBS, or the Earth Radiation Budget Satellite. Designed for a 2-year mission, ERBS will use onboard instruments to precisely measure the energy levels of Earth's atmosphere. This is just one of a 3-satellite network, the others being launched by expendable rockets, to watch how the Earth both absorbs energy from the sun as well as radiates energy out into space. What is the average monthly energy budget for our planet? What is the seasonal movement of energy from the tropics to the poles? What are the trends in all of this data? And what does that tell us about where our planet is headed? Also being flown into space is the Large Format Camera, or LFC, that got bumped from STS-41D. Right on time, 7:03 a.m. Eastern Daylight, October 5th, 1984. On the first attempt, Challenger nails it.
We have main engine start, 5, 3, 2, 1, 0. We have SRB ignition and the history's largest astronaut crew is on its way.
Roll program.
Roger, roll.
Just 9 hours in, Ride grapples Herbs with the RMS arm, maneuvering it into the deployment position, and lets go.
Roger, Dave, and the payload is unlatched. We had double motor drive times on all latch motors, and we're getting ready to unburn.
Roger, we copy.
Okay, looks like it started to move out a little bit. It's coming. It's trying. We got it out a few inches anyhow, and it stopped.
Roger.
And that got it. It looks like we've got it loose and it's fully deployed.
Challenger, Houston, you're go for release.
Okay, we'll put it in work.
And we have a release of the Herb satellite.
Okay, Sally's back in the arm off of the pin at this time. And we'll stand by. The arm's a good machine.
Roger, we concur.
And Dave, I guess if you can't deploy over Kansas, California is the next best thing.
We use the arm to lift it out and deploy it, and this was the first of our trials on orbit. It has a couple of solar arrays, and the first time that we tried to deploy those arrays, things didn't function exactly normal. Did run into some kind of problem, which was probably thermal associated, and the persistence of the ground coming up with new ideas to way to warm it up, and Sally stroking it nicely with the arm, it managed to get out. And this shows the deployment sequence as she pulls the arm away, and the satellite is up and functioning well.
Challenger pulls away, and Herbs is free to begin its own climb towards its operational orbit. Designed for a 2-year mission from its deployment in 1984, Herbs lasts until 2005. It provides crucial data on the depletion of ozone in our planet's atmosphere, a side effect of the pollution of our atmosphere with complex aerosols known as chlorofluorocarbons, or CFCs. These halogenated hydrocarbons, such as old-school refrigerants, solvents, and blowing agents for foams and packing materials, maliciously siphon the ozone layer away via chemical reactions, increasing rates of cancer as a result of increased exposure to UV radiation emanating from the sun. The chemistry is clear and undeniable. Herbs data contributes to the passing of the Montreal Protocol, an international treaty that leads to the banning of entire classes of CFCs and their production by industrial processes. The ozone layer, as a direct result of this action, is healing. It will return to 1980 levels sometime between 2040 and 2066. A rare example of a landmark success in international action combating climate change. Data-driven analysis by NASA and NOAA satellites help provide us with a clearer picture of our world and tell us how our planet is evolving, even if we have a hard time agreeing on what the solutions may be. Knowing the bigger picture is the first step. As the mission proceeds, the crew operates the ground-penetrating radar. However, a malfunction in a motor-driven antenna leads to an annoying reality. They can't effectively live stream data back down to the ground. Working with their limited capacity onboard tape, only 40% of the potential data was actually captured. Even still, fascinating discoveries abound. The field of archaeology got an unexpected boon when data from SIR contributed to the discovery of an ancient, abandoned city in Oman, buried beneath the sands of time, lost for thousands of years, no more. Sally Ride has to use the RMS arm to push the antenna panel back into the closed position as further malfunctions occur with the radar platform. Challenger had entered an initial orbit of 218 miles or 350 kilometers. Over the course of the next few days, the crew deliberately lower its orbit down to just 140 miles or 225 kilometers, barely scraping the top of our planet's atmosphere, to provide maximum proximity for the Earth-observing instruments aboard.
First, when there's nothing but a slow, glowing dream that your fear seems to hide deep inside your mind. All alone I have cried silent tears full of pride in a world made of steel, made of stone. Where I hear the music, close my eyes, feel the rhythm, wrap around, take a hold of my heart. Wanna feel it.
Good morning, Challenger.
Hi, this is the 41G crew. We're not in right now, but if you leave your name and number, at the sound of the tone, we'll get back to you.
Roger. Blaha, B-L-A-H-A, 713-483.
On flight day 7, Liestma and Sullivan prepare to go outside, ready to tackle their fuel transfer experiments.
The EVA will begin at 10:33 a.m. Central Daylight Time when astronauts Kathy Sullivan and David Liestma leave the airlock and enter the payload bay to perform their orbital refueling system transfer operation.
Ah, look at that. See that? You got it? I think that's the last piece. Voila.
Je ne comprenez pas.
Comprende West Virginia?
Oui, oui, West Virginia, oui, oui.
Where's my favorite MCM? Can you swing around for IMAX? Like that? Hey, I see Max. Is Max behaving now, John? Not very.
The suits have really accumulated a very superb track record in the last couple of shuttle flights with EVAs, and they were just a delight and a great confidence factor to use. Those suits weigh about 225 pounds on the Earth, and it would usually take some combination of Dave or John or I to move one around in the training sessions. They're just a breeze on orbit. Zero-G is a wonderful thing, and they're really pretty comfortable devices as pressure suits go to work in. Dave at this point is passing across the handrails that go along the forward bulkhead of the orbiter's cargo bay and getting ready to go aft to where he'll lock his feet into a foot restraint and start doing the hydrazine refueling task, which you see in progress here. And I picked up a set of tools that we needed to supplement that and came back and joined him primarily to assist and document, and both of us making sure that neither of us forgot anything along the way.
This facility actually simulated a connection or valve connection that is flying aboard the Landsat satellite to prove that we could go up and make a connection with that type of device and actually transfer hydrazine or refuel it on orbit. And in my opinion is the next major step in doing what we're going to be doing in the future, and that's satellite servicing.
Okay, John, here comes the verification test.
I think we can see both pins and sockets. David at the forward bulkhead just inboarded the boom, and I took your advice and came across the pallet. I'm forward on the handrails outboard, and we can see both the pins from here, and the dish is so loose on both gimbals right now that I'm not sure that we're precisely positioned, but we can tweak that as we go, as Sally and Crip drive the pins. I think we're in good shape. Coming, Crip. Keep it coming. Keep coming. Give us short bursts. Keep going. Got it. We're home.
Let's go.
We're home.
Driving all the way. Okay, we'll keep rapping. Okay, we're
in. And I'm ready on the second one. Second one's in too, Crip. We're pinned.
It's totally pinned. I can confirm the top one's totally locked. And the bottom one looks locked too.
I can confirm them both. We got them.
Okay, both appear to be locked.
Both are
They're
locked.
both locked, Crip. They are locked. Do not appear, they are locked.
We had another failure in one of the orbiter's communication systems on day 2 of the flight that was a potentially severe impact to especially the radar experiment. And in an attempt to get around some of that impact and lessen it, we were asked by the ground while out EVA to go and manually reposition this communications antenna that you see there and set it up so that locking pins could be driven into their slots, and we could fix it so that it would come back into the orbiter's payload bay on entry day, and this would allow the experiment another day's operations on orbit once we were certain we could close that antenna back up when we needed to. Additionally, since we had some problems with the SIR-B radar antenna, I was asked to take an inspection tour, as it were, while we were out in the payload bay and make sure that all the different leaves of the antenna were stacking correctly when we folded it up. And that fortunately also proved to be the case, so as you see here, Dave waiting a little bit after the pallet so we could keep our tether lines clear, and I coming back up from looking at both antennas. We've managed to put 3 tasks together successfully on the EVA and set ourselves up very well for another day and a half of productive operations on orbit.
Their EVA lasts 3 hours and 29 minutes, a resounding success.
Right now we're orbiting down over California, so there's not too much ocean, but one of the things I would like to talk about is 2 revs ago we came down through New England and came over Long Island Sound, then Long Island. As soon as we got over the edge of Long Island, there was a whole stream of spiral eddies that went right down the eastern shore of Long Island, and then as we orbited further out over the Atlantic, there was a whole series of long internal waves, and they drew my attention to an interesting factor, and that was that when you looked down carefully, you could see a color change over the ocean, and that indeed was the north wall of the Gulf Stream. So I think for the first time we've seen a whole packet of very long internal waves associated with the north wall of the Gulf Stream. Interesting thing was that these particular waves were inboard of the north wall, in other words, in the Gulf Stream itself. And this combination of spiral eddies outside the Gulf Stream, the main Gulf Stream, and then long internal waves inside the Gulf Stream, I think is a combination that's never been seen before. I think that's one of the exciting things that has happened on this trip. That would just happen two revs ago. For some years now, the astronaut crews have brought back photos of the ocean from space, and which sort of captures small areas. But when you come up here, you see that all those small areas and all that dynamics are all interrelated. And for example, literally the whole of the Mediterranean is just one vast eddy field. It's spiral eddies all the way.
On October 13th, Challenger heads home. She's been cleared for her second landing at Kennedy Space Center in Florida.
Orbiter Challenger now approaching the Kentucky-Tennessee line. First roll reversal beginning right here over Knoxville, Tennessee at an altitude of 174,177 feet. Mach 11.35. Standing by for Mila acquisition.
Challenger Houston back with you through Mila. Configure AOS.
Okay, you're still configured.
Challenger will pass over Brunswick, Georgia on the Florida state line as it heads out over the Atlantic Ocean to approach the heading alignment circle at KSC for a left overhead 190-degree turn into runway 33. 118,000 feet now. Range 138 nautical miles.
Challenger Houston on glide slope. Surface winds 330 at 8.
8 knot surface winds at 330 degrees. Velocity 494 feet per second. Altitude 1,100 feet, 800 feet. Range 1.3 nautical miles. Gear down. Touchdown. Mission Control, Houston at 8 days, 5 hours, 24 minutes. The largest crew in the history of spaceflight is home.
Houston Challenger, we're well stopped.
Challenger Houston, we copy that, Crip, and you outfoxed us again. You landed at KSC, but the beer's been sent to Edwards.
Once on the ground, the crew discovers more missing and damaged tiles on the underside of the orbiter, a highly concerning development. NASA engineers traced the lost tiles to the waterproofing that eventually led to the debonding of several tiles on the orbiter's skin. They would ultimately remove and replace some 4,000 tiles on the orbiter body. Hot on Challenger's heels is the orbiter Discovery, ready for its second mission in space. It's less than a month away from launch, a record-breaking pace for the program. This is not Discovery's original second mission, whose payloads were already merged with its first. In fact, this last-minute mission wasn't even on the books until just a few months ago. STS-51A, the first flight in fiscal year 1985, but the final one of calendar year 1984. Remember those 2 satellites in the beginning that fizzled out and failed to reach their target orbits? NASA is gonna go get them back. That's right. Far from letting a disappointment blemish any part of the shuttle program, the orbiter Discovery, borrowing the 2 jetpacks from Challenger, is going to fly into space to retrieve the 2 failed satellites and bring them back home for repairs. The satellite insurance industry is a fascinating ecosystem that is little talked about in the field of space exploration. Satellites are important commercial assets, and many of them do have their own insurance policies. At several $1 million a pop, satellites are expensive machines. Palapa B2 and Westar 6 are covered through the Lloyd's of London insurance market. STS-51A, which is being partially funded by Lloyd's, is an attempt to recover these 2 valuable vehicles. It's never been done before, but a success would revolutionize risk management in the space sector, and NASA is keen to prove the robustness of the shuttle platform, and in particular, they seek to redeem the MMU after the mission to Solar Max. The Indonesian government is holding on. They fully intend to maintain ownership of their satellite and relaunch it in the future if possible. Western Union, however, is divesting itself of its telecommunications assets, and Westar 6, if recovered, will be sold to AsiaSat, a Hong Kong-based company. First things first, NASA and a couple of brave astronauts with MMUs need to go wrestle some more satellites in space. Controllers on the ground are able to reduce the 2 satellites' orbits from 600 miles or 970 kilometers to just 210 miles or 340 kilometers, well within the shuttle's range. There was only one problem. Yup, they're spinning. The good news, however, is that they're spinning along an axis that may prove fortuitous. It's a highly stable spin, and the engine bell of the fizzled solid rocket motor is rock solid, a perfect target. The receptive T-pad docking system will not work on the Hughes HS-376 design. Instead, NASA has to invent a new, much more intimidating device. This is the Apogee Kick Motor Capture Device, also known as the Stinger. Mounted on an astronaut's chest, they'll fly the MMU up to the spinning satellite and impale its engine bell with the protruding spike. The astronaut will slow the satellite's rotation, and the shuttle will close in. A robotic arm grapple fixture will allow the operator inside the shuttle to grab the satellite and secure it on a mount inside the payload bay. Simple, right? If successful, this promises to be one of the most fantastic missions in the history of the shuttle program, with 2 rendezvous, 2 satellite captures requiring 2 untethered spacewalks, and a litany of the fantastically interesting science we've come to expect. But it doesn't end there. Discovery has 2 satellites of its own to deploy. Another HS-376 called Anik D2 for a Toronto-based aerospace company, and will be used by Telesat Canada to provide voice and data traffic, offering Canadians in remote regions live coverage of parliamentary debates, cable television, and communication services. Like the other HS-376s, its final rotational velocity is 50 RPM, and it will use a solid rocket motor to help boost itself into a stationary orbit of the Earth. The other satellite is SYNCOM 4-1, the large, unclassified military communications satellite that was swapped out of Discovery's first mission earlier in the year. Its faulty transistors have been replaced, and it's ready to join its sibling in the sky. 2 satellites out, 2 satellites in. Crew of STS-51A, in yet another social reference, style themselves the ACE Repo Company. The commander is Frederick Hauck, veteran of STS-7, making his 2nd trip into space. Pilot, David Walker. Mission Specialist 1, Dr. Joe Allen, 2nd-time shuttle flyer and astronaut since 1967, having worked the Capcom console for many Apollo-era flights, including the moonwalks of Apollo 15. Mission Specialist 2 and Robotic Arm Operator, Anna Lee Fisher. Mission Specialist 3 and Joe Allen's spacewalking partner on this flight, Dale Gardner. A launch attempt on November 7th is waved off at T-minus 20 minutes due to high wind. On November 8th, 1984, Discovery lights up the morning sky.
T-minus 1 minute.
The hydrogen igniters under the orbiter's engines have been armed. These devices are used to ensure that any hydrogen flowing through the engines does not accumulate. T-minus 45 seconds. We're just 18 seconds away from switching command of the countdown from the ground computers to the onboard computers. T-minus 15, 14, 13, 12, 11, 10. Your go for main engine start. 7, 6. We hit main engine start. 3, 2, 1, and liftoff. Liftoff of Discovery and the first flight to retrieve and return satellites from space, and the shuttle has cleared the tower.
Tower clear. Roger, roll. Roll program initiated. Houston now controlling. Roll program completed. Beginning throttle down to 89%, then to 67%. To pass through the period of maximum aerodynamic pressure. Throttle down to 67, confirmed. 45 seconds. Downrange distance 2 nautical miles. Altitude 3.9 nautical miles. Velocity 2,200 feet per second. Beginning throttle up back to 104%, the nominal throttle setting for this mission. Throttle's coming up. Engines at 104%.
Discovery Houston, your go at throttle up.
Roger, go. TC less than 50.
Velocity 8,000 feet per second. Altitude 53 nautical miles.
Discovery Houston, negative return.
Okay, negative return.
Discovery Houston, press to ATO.
Roger, press to ATO. We got me go 25-7 up at 280.
We copy.
Normal main engine cutoff confirmed.
Discovery Houston, nominal OMS 1 targets, APU shutdown on time.
She was doing much better on her second mission. Only one issue, another monitor failure, this time involving CRT-4, occurs. One day, 8 hours and 49 seconds after launch, the Canadian Telesat is deployed.
Discovery Houston, the orbiter and ANIC are looking good for deploy.
Roger that, Ron. We concur.
And the terminal sequence has started.
Okay, we've got good news. The deploy went without any problems at all, on time.
Okay, we're going to let this run, David, so you can see the Omni deploy, and then we'll switch over to the PKM.
Flight days 2 and 3 pass without incident. Minor orbital maneuvers being made to catch up with the first malfunctioning satellite, Palapa B2. The crew deploy their second satellite, Syncom 4-1, and the 7-ton beast lumbers out.
Flight day 3, we deployed the Syncom satellite, called LESAT sometimes, similar to what you saw this last spring on 41D. It's a large satellite, as you can see, comes out in that frisbee fashion that we've talked about before. It's about 14 feet in diameter and weighs 13,000 pounds. And it really looked large to us as it came out of the payload bay. Very slowly also, as you can see, only just a little over a foot per second departure from the bay. The one nice aspect about the Syncom deploy is that we punch it out down towards the Earth in the attitude we're at. So as it leaves the bay, and you can see here, we have a beautiful view of the Earth down below as the satellite departs.
Both satellites' Discovery releases hit their burns right on the mark. Everything is going to plan. The crew prepare the onboard spacesuits. They discover the left side helmet lights are totally dead. Their switches had been left in the on position and the batteries were completely discharged. The crew fixes the problem and moves on with their mission. Such is the rhythm of working in space. Problem, solution. Problem, solution. On flight day 5, the shuttle closes in to the first satellite. It's game on for Allen and Gardner, with Fisher assisting on the robotic arm. Houck and Stewart flying the orbiter.
Houston Discovery, we're going MET-0 for the EVA now. They're going to power to bat.
Roger, copy. We'll call it 0110.
Roger that.
And Dale, it is right there, my friend. Great. We could go get it right as she stands. You could let me out on a cable, I could grab it. Gorgeous. How are we going to grab that? It's too smooth and steady. That's your job.
Joseph, are you at the MMU?
That's the firm.
Good.
This is Mission Control. They're progressing very well with the EVA, preparing to do the flight check with the Stinger on the MMU.
Allen dons the MMU and flies out towards the satellite, his Stinger at the ready. The Stinger is more complex than it may outwardly appear. It is able to freely spin and has brake pads operated by the astronaut, which can be used to gently halt the rotational momentum of the target.
Wow, look at that. Houston Discovery, the sun is up and we're ready to go.
Roger, copy that, David. We're ready also.
Okay, I'm lined up pretty well behind it. Starting into it. Okay, I'm penetrating. Goggles full. Soft dock. Crank. It's pulling it right down. I'm using no gas at all.
Allen cranking down a ratchet handle to tighten up the grip on the Palapa satellite.
Okay, the wrench is broken over. Stop the clock. I've got it tied.
Okay, at home now.
Mark.
He nabs the errant satellite and restrains it. Fisher moves in with the robotic arm.
And the RMU officer reports moving the mechanical arm in for the docking.
Take it out in, Anna. You got plenty of room. Okay, Joe, she's got 5 feet to go to the grapple fixture. I'm watching her in my wrist mirror. Like a hawk, and now I can see it. Looking perfect, Anna. Cycle gyropower. It cycled. Looking perfect, Anna. We have you, sir. There's a hard grapple. Good work, cabin. Way to go. That doggy's on the ground, and we're putting the rope around its feet.
Gardner will be moving into the A-frame installation here in a few minutes.
David, are you there?
Yes, sir. Go ahead.
My gloves, I would guess, are 120 degrees inside right now.
Okay, the sun will be going down shortly. That should help you.
Good.
Gardner is on standby. The astronauts need to remove the satellite's omnidirectional antenna to reduce its profile and clear space for the installation of an A-frame. This structural antenna bridge bracket will allow Fisher to grapple the satellite from above, giving her the required leverage to install it in its receiving mount inside the payload bay. But there's a problem. They can't seem to get the A-frame attached to the satellite. Without it, the robotic arm cannot be used to secure it to the shuttle.
Yeah, what we'd have to do is to get out of the configuration we're in, get the A-frame put away.
Want me to tell him?
Yeah. Houston, Discovery, we're going to let Dale talk. We got a problem here.
Roger, go ahead.
Okay, Jerry, here we go. The common bracket clamp will not fit on the satellite. The problem is, between the two octagons, between the two common bracket parts of the satellite, is a structure that's sticking out far enough that it is hitting the cross brace of the common bracket clamp before I can get the V-head bolts even close to driving onto the octagon. And it's not a piece of structure I can remove. It is massive. I've tried twisting, as you can imagine, every direction. I've tried forcing it on. It's within maybe an eighth to a quarter of an inch of making it, but unfortunately close doesn't count with the common bracket.
Okay, understand that, and what are you proposing to do?
We are proposing to go to the no A-frame procedure, and I will go up to the PFR in the forward pallet and try the technique perfected by yourself. I'll have Anna hand it to me. I'll grab the top end.
Okay, we copy Plan B and proceed.
Very thick, heavy metal. Oh yeah, see that thing? Yeah. That was hitting across me. It's enormous.
In a complete role reversal from the story of Solar Max, where the robotic arm had succeeded where humans had failed, this time the humans jump in. Alan uses his hands to hold the satellite steady as Gardner removes the stinger, and working together, the pair gingerly pivot and maneuver the unwieldy cylinder into place.
I take them for a wrist tether. I have one. Oh, I know, but I've been doing it with this mini workstation. Oh, yeah. It's just, it wraps around itself and it dangles and... Okay, now be real gentle, Dale. Yep, I got it. Okay, you sure? I've got it, Joe. Okay, I've let go of it. Okay. Okay, here it comes. 2 degrees a second.
Gently, Dave. Dale.
I just gave it a touch, Dave. That's about my lowest bid. Well, Jerry, we're going to try to put her home here. Okay, watch number 1, please. Quick. All right, we got her. Now, do you want me to move across? Did you get yours too, Joe? The big latch yours? Mine's latch. Okay, yes, Joe, you can move across. If you got 2, you can latch the third, guys. You have it ready back there? Oh, my goodness. Joseph. Got him up.
3 latches down and locked.
Snap, click, bang. Palapa B2 is home free. They had done it. This was an important win for the human body over the machine. The shuttle program's very own John Henry triumph. An astronaut and their hands demonstrating once more the power of improvisation in space. After 6 hours, Allen and Gardner head back inside, their first major hurdle now cleared. Morale is high, and confidence grows in advance of the second recovery.
Okay, Dave, I guess where we're at right now is with, I think it was Plan 2 that you all talked to us about last night, which is, you probably guessed from Rick's discussion, using the MMU to stabilize the satellite, and then having the other guy get into the MFR on the RMS, grab on the antenna end, point it down into the bay over the forward pallet, have the first person clicked off the MMU and do as we did yesterday, but now in a better position, obviously, take the stinger off and put the adapter on and berth it from there.
So we've learned an awful lot in the last 24 hours about what our capabilities are in the contingency world. And so in some respects, we know more in real world about the off-nominal than we do about the nominal. And I think we could do it. There's no question. And if that were the decision, we'd press on and do it that way. It seems to me now that there are more uncertainties and perhaps a bigger hit to the timeline if we go with the nominal.
Flight Day 6. The crew rest and reset as Discovery laps the Earth in pursuit of Westar 6. A quick check of shuttle systems reveals the aft payload bay lights have stopped functioning. A minor annoyance, but not an obstruction to the mission, as the forward lights were still working. The pair would forego the installation of the antenna bridge structure and repeat their manual mounting of the satellite in the payload bay for Westar 6. Flight Day 7, the second EVA.
Oh, wow, look at that satellite. Oh. You know, if the bottom were threaded, Rick could just drill it into the pallet. He wouldn't even cross-thread it. Okay, I'm going to use one of the rollers up there as a target. Here I go.
This time, Gardner flies out, while Allen positions himself on the mobile foot restraint on the robotic arm for better positioning.
Oh, it flies nicely.
Gardner now going after Westar.
Going for toggle. Hey, toggle, I got it. Cycle, gyro power. Hey, cycle. Well, I gave it a good knock. Perfect. Perfect.
Oh, you just lost a wrench, Dale.
Where'd it go?
It just came off the tether.
Where did it go?
It went towards the payload bay, or towards the cabin, up against the forward cabin bulkhead. Can you see it?
Which wrench is it? I don't see anything.
It was the torque wrench.
Joseph, I'm going to let go now. You got it. Okay. I'm going to go back to the aft starboard. Is that what you want next?
Houston, Discovery.
Go ahead, Discovery.
Roger, we have 2 satellites latched in the bay.
Roger, that gave us a big cheer down here.
The astronauts use the Omni antenna on Westar 6 as a handle, and the pair easily bring the satellite into place, much smoother than the first time around. It was a complete success. Gardner pulls out a sign, a tongue-in-cheek moment that will become one of the defining memories of the Space Shuttle program. The pair head back inside after 5 hours and 43 minutes. The mission of STS-51A was complete. There was only one more thing left to do.
Can I just say, Joe, you and Dale deserve a lot of credit for retrieving those satellites. You know, we've got a little gym here at the White House, and I pump a little iron whenever I get the chance, but I don't know about that satellite lifting. Maybe that'll become a new high-tech Olympic sport.
President, that man maneuvering unit worked perfectly for both Joe on the first EVA and for myself on the second. The docking with the satellite and capture was exactly as we had trained to in simulators in the ground. It was a real pleasure doing it.
That's just great, and we were all keeping track, and everyone down here rooting and praying for you. You've demonstrated that by putting man in space on board America's space shuttle, we can work in space in ways that we never imagined were possible. Bless you all.
Just prior to re-entry, a window aboard Discovery suffers a high-velocity impact, penetrating the outermost layer of glass down to a structural margin of 24%. Shuttle windows have 3 layers, each designed for a different purpose. The thickest of these, the middle or so-called pressure pane, is 1.3 inches or 33 millimeters thick. Window impacts are an unsettling fact of life for the shuttle and all manned spacecraft. In some cases, the windows can be flipped over and installed in the opposite position. In other cases, they are replaced entirely. No windows would ever fail in the 30 years and 135 missions flown by the space shuttle.
Lots of pink stuff outside the windows.
Is that right?
Yeah.
Discovery now entering the heading alignment circle, a 304 degree left overhead turn. Max G is 1.5 on the hack.
Discovery Houston, on glide slope, on centerline.
Roger.
Wheels are down. And locked. We have touchdown. Nose gear now coming down. Touchdown. Discovery now rolling out, runway 15 at the Kennedy Space Center. After a 2.5 million mile service call, the crew of 51A is home.
Discovery makes her first landing at Kennedy Space Center, rolling to a stop and closing out calendar year 1984 for the American human spaceflight program. We had seen the rise, fall, and rise again of the MMU, the masterful utility of the robotic arm, and the contribution of the shuttle to both science and commerce. Through it all, humans were there, paving the way to the future, each mission adding one more brick in the foundation of our species' knowledge and experience. 1984 will endure as one of the most exciting years in the shuttle's history. STS-51A would, however, be the last time an MMU was used on a mission. Bruce McCandless and others would continue to lobby for more MMU flights and seemed to come close in 1988. But ultimately, the Department of Defense's involvement in the shuttle program would decrease over time, and satellite repair and refuel would not become a primary driver for shuttle missions, as many at NASA had hoped it would. Jetpack missions came and went in the blink of an eye. After just 3 flights, the robotic arm and the mobile foot restraint would enjoy a monopoly on EVA strategy. The MMU would lead to a miniaturized emergency thrust system called SAFER, or Simplified Aid for EVA Rescue. Still active into the modern age, this cut-down version offers a single, last resort push for astronauts who have somehow broken free of their tethers. It has never had to have been used.
Dave on orbit described Dr. Allen as large in personality but diminutive in stature. Whenever his personality got a little bit too large, we would stuff him away in a locker for a few hours, and then when a task needed to be done, it was my job to go down and get him out. This was a somewhat unpleasant task for me, but Joe seemed to like the freedom at times. And
the hard part was putting him back in there again later once we got him.